Thank you for being here. Thank you for attending my talk, especially that this is the last one of the day. So I assume you still have some energy to listen to what I have to say. Today's conference actually started with the HoloLens talk, where Paweł and Piotr introduced us with the technology. They showed us what is it capable of, and they showed us also some nice applications. And my talk, on the other hand, is going to be also about HoloLens. But in particular, I'm going to focus on one special feature in HoloLens called spatial mapping. But let me first introduce myself. I'm Rafał Legiędź. You can find me on Twitter at Rafek. I'm a software engineer. I work for a consultancy company called SolidBrain, based in Krakow. What I do, I mainly focus for the last 6 months on those AR experiences that we can get with HoloLenses. So I explore the opportunities. I talk with different businesses to find out where and how can we apply this technology. Also, I'm a conference organizer. I'm involved in a conference called DevConf since 2011. That's in Krakow. And also, I try to be a conference speaker, so whenever I think I have something interesting to say, I apply for conferences, and hence I'm here, for example. So HoloLens. I can safely assume probably that majority of you already know what this device is all about because of the morning session and because of the fact that we do have a HoloLens booth outside. So I'm not going to ask you to raise hands because I assume you already know that. But in addition, I would like to say that this device is not that very new because it was 2015 when it was first announced. Then it was released in 2016, and first wave of devices was sent to developers in June 2016. So it's been a while since it's on the market, and lots of developers actually embraced that technology and already delivered lots of applications. So long story short, this is a very sophisticated AR device. You put it on your head. You have optical see-through lenses, so you can still see the world. You fire the app, and you can see holograms all around you. And by sophisticated, I mean that this is nothing like anything that already is on the market. I mean, the holograms and the whole experience is very immersive to the user. The holograms blend in a pretty seamless way with the environment, and we will see in this presentation how is that possible. Also, it's a self-computer in itself, so it has batteries. It doesn't need a connection to an external computer or anything like that. It runs Windows 10, and it's pretty much it, briefly. So having all those AR and VR devices on the market, we might want to ask some questions where the HoloLens actually lives in this space, especially that VR is huge right now as well, AR as well, and guys in the morning already showed us how VR and AR differs. So where HoloLens is in this spectrum? So we have those two realities, the physical one that we interact with on our regular daily basis. At least I assume we interact with it pretty regularly. And on the other hand, we have this digital reality, right, where everything is virtual. And between those two realities, we have the whole spectrum where different experiences exist. So for example, current AR solutions live somewhere very near that physical reality. What I mean by that is AR that we might be most familiar with are solutions that exist on mobile phones or tablets. And basically what we see while using those solutions are whatever the camera lenses of the device can see, and on top of that picture on the device, there is this digital content overlaid. So and that's it. And there's basically no immersion effect for the user. The user is still fully aware of the physical environment because he or she only holds that little device in front of it, him or her. So there's very little immersion there. There are some more sophisticated ones, devices. I mean, for example, aforementioned Project Tango at the first session, where we have a little bit more environmental understanding for the device. Also, we have some wearable devices like Google Glasses, which was killed and then it was reborn. Epson Move Vario, for example, those are wearable devices, basically lenses that the user can put on his or her head. But basically, those solutions deliver some kind of static AR experience. What I say by static is that basically we have some kind of digital content rendered just in front of the user eyes, and basically those are usually some kind of steps, some manuals, etc. Those informations are really are not really attached to anything in the user's environment. So all AR solutions that we might know lives very near this physical reality. On the other hand, we have the digital world and where all the VR experiences live. And we might be familiar with the most popular ones, which are Oculus Rift from Facebook or HTC Vive or PSVR from Sony. And those experiences are, wherever you put it on your head, you are basically detached from the physical reality. You basically are transformed to the virtual world, like fully, without not sense at all of the physical reality. So those experiences live very near that virtual reality. And you can actually find a lot of funny VR pranks videos on YouTube where someone is playing on a VR game and someone else is poking that person, and this person with VR headsets freaks out. That's because how much the mind is tricked into that virtual world. So HoloLens basically lives somewhere there. As I mentioned before, it's an AR device. It's a very sophisticated one. And sophisticated, by sophisticated, I mean that it can really, it can blend this digital content pretty well with the user's environment. And we will see how this user environment is being scanned and incorporated into the applications. So, and also the HoloLens is a wearable device, so the user can go hands-free, and it has optical see-through lenses so that the user is still aware that is somehow part of the physical environment, but still the digital content is pretty seamlessly composed into the user surroundings. So we might think that this really brings some more, where it gives us really immersive experience when it comes to AR. And also it's worth mentioning that what Microsoft is doing right now within the AR VR world is basically what they released not that long ago, and I mean it was 17th of October. They released a whole set of new VR headsets. I don't know if you have heard about it. How many of you have heard about Windows Mixed Reality headsets? Quite a few people. Yeah, so it's worth explaining. Basically what they did is they partnered with some other companies like Asus, Acer, Samsung, Dell, Lenovo, I don't remember, like several of them. They constructed the regular VR headsets like you might know from as Oculus or Vive, but they incorporated some technology from HoloLens in those headsets, so that, namely the inside-out tracking, so that those new VR headsets can track their position in the world by themselves, so they do not require external sensors like Oculus or Vive do. So they bring the slightly better VR experience to the user, so that it's somehow better than what Oculus or Vive give us. And I think the grand plan here is that Microsoft is trying to fill the whole spectrum by releasing one or maybe a family of products that could deliver different kind of experiences that lives in within that spectrum, and that spectrum is called mixed reality, and Microsoft is using this term a lot recently. But this is not the term that Microsoft came up with. That's basically this term showed up in papers like 40 or 30 years ago, so it's nothing new. You might also find the other name for this spectrum, which is called reality-virtuality continuum. So okay, let's talk a little bit more about HoloLens itself, what's inside. So first things first, sensors. It wouldn't be possible, the whole magic wouldn't be possible without some sophisticated sensors that are inside. In the context of this session, the most important ones are the environmental understanding cameras, which are here. There are 4 of them. And they're responsible for scanning the user environment. And they're doing it constantly. I mean, as soon as the device is fired up, they scan the user environment. We can't stop them, basically. Among others, there is a regular RGB camera, mixed reality capture module, the depth camera, ambient light sensor, and also an array of 4 microphones. That's for the user voice commands. Next thing, optics. So I'm not going to go here into very details, but those are optical see-through ones so that the user vision is not occluded by anything. And every eye is powered by an HD engine, so that it roughly has a resolution of 1200 by 700 something per eye, but we do not describe HoloLens in terms of like regular resolution as we might know from regular screens, because with HoloLens we have every pixel rendered by the real world, right? So we don't have to fill the full screen with pixels, so there's no reason to reason about it in terms of like pixels on a regular screen. Instead, what we need to worry about is that how many light points can we render at the given moment. And light points are those points that build up holograms, so those 3D objects that we can see through HoloLenses. And HoloLens is able to render 2.3 million light points at the given moment. And the other thing is density. We might know DPI from regular screens that tells us how packed the pixels are on the screen. And here we have something which is called holographic density. And that means how many light points per radiant can fit on that holograms. And HoloLens is able to fit 2.5K light points per radiant. The other thing, holographic processing unit, also called HPU. This is the core of the computation when it comes to sensory data. So it gets all the sensory data and processes them so that the main CPU isn't bloated with work. And also it's a customly designed especially for HoloLens. It also reads user gestures, for example. And you might have heard some news in the media that the current vendor of this chipset actually stopped producing it, and I think it was Intel. And that might be a little bit worrying regarding the future of HoloLens, but Microsoft already announced that they're working on the future version of this chipset that would actually include some AI modules as well. So that might help us thinking that the HoloLens V-Next will be even more interesting device. So given that all this technology, there has been lots of work put into different projects. And to just name a few that are in the market, I'm going to go through four of them. I mean, those are the most popular one. And actually for everyone you can find a video on YouTube and see it more detailed. So the company, Citi company created some kind of a financial app for traders, I think, and where the user can actually render some financial data in form of 3D objects in front of him and operate it with gestures, also dig through those data and render some nice 3D graphs. The other thing, Ford recently announced that they're using HoloLens for design purposes. So they're enhancing the design process with HoloLenses. And here we can actually see that those two men actually wear HoloLenses and they're working on the same hologram. And that's what we actually saw at today's morning session, that several people can work on the same holographic space. The other thing, Schneider Electric, this is a very cool video, by the way. If you Google Schneider Electric video HoloLens, you will see that video. This is a very nice application. Basically, that's the application for service workers that are doing some maintenance work on appliances. And whenever the worker comes to the machinery that he or she is going to do some maintenance work on, he will have some digital content rendered, overlaid over the machinery, so that there are some tips, some workflow being rendered, so that the user can simply follow it because the user has the hands-free and do the work which is enhanced with this digital content. And the last one is the application from the company called ThyssenKrupp. It's the company that produces elevators, and it's also the maintenance application for service workers. So whenever the service worker has some job to do on an elevator, he can display some contextual information regarding that piece of machinery, and can have some videos, some actions, some service manuals, some 3D object of the thing that he or she is going to work on rendered, so that can explore it a little more deeper without touching the real one. Also, on the video on YouTube, we can see that you can do like a Skype call and consult some things with someone at the office. So those are all cool applications and probably really useful, but they do not use HoloLenses to the full extent. I mean, they do not use these spatial mapping capabilities. And there are some, I mean, there are a lot of applications that use spatial mapping, but there are 3 of them which were released along with the release of HoloLens that shows how spatial mapping is really helps delivering this immersion effect with blending the digital and the real world. So first is the game called Young Conquer, where we have this guy running around your room and actually runs on your floor and jumps on your sofa, on your chair, on your table. It's really awesome. And the other one, my favorite, it's a game called Fragments. How many of you have actually played this game? Not many of you. So my advice would be just whenever you have next time whenever you have HoloLens in your hands, just play this game, because it's really, really awesome. And what it does is basically it transforms your room, your location where you're at, into a crime scene. And basically you are a detective and you are trying to solve some case. And the clues for this case are actually hidden in your room. So you actually walk a lot within your room and looking for the clues, and you feel like a real detective actually. And also you have some holographic persons which are like full size, and they're walking around with you, they're sitting on your sofas. It's really, really immersive. I strongly recommend playing that. And also the other game called Roboraid. There is this alien invasion in your room, and aliens are drilling through your walls like real wars, and they are running into your room, shooting at you, and you can shoot them, and if you miss-shoot them, you break your real walls actually. And this immersion effect in this game is really awesome as well. So how is that even possible that we have this kind of cool features? So this is all possible because of spatial mapping capabilities of HoloLens. As I already mentioned, whenever the device is turned on, it starts scanning users' environment. And I mean that. I mean, you don't even have to fire any special application on HoloLens. As long as it's turned on, it keeps scanning. If you put it aside, but it's turned on, it's still scanning the environment. So that's pretty awesome, and a little bit scary, of course, because it's gathering data all the time. And so this is happening on operational system level. It doesn't do anything with your app, what I mean. And what operating system does, it stores all the information, all the environmental information inside some kind of buckets inside the operation system. And those buckets are called spaces. So whenever the HoloLens is turned on in a new location, and that the HoloLens doesn't know, HoloLens doesn't detect that it's been in this location before, it creates a new bucket, calls it space something, usually put, if it knows the Wi-Fi SSID, it puts it there so that we can identify it later a little bit easier. And it starts gathering data and it puts it into that bucket. And whenever we take the HoloLens to other location, it will detect that that location differs from the one before, and it will create another bucket. And when we will go back to the location when we have already been, then it will probably, I mean, most of the times, it will detect that you already been to that location, and it will start updating data that it already gathered inside this location. And whenever HoloLens is confused about the location that it's being fired in, it asks the user that I'm slightly confused. I think it's maybe space 7 or 6. I'm not sure. Help me out and pick the current solution or current location, or just create the new one. And the thing is, you might start asking questions that, can we view those data? Because that was something I was trying to do at the very first time, because I can see that that data is here, but I would like to see this data. I would like to see what's under space 4, how much data is here, and how does it look like, right? So what I can say, we cannot. I mean, we cannot go here and click through those spaces and see how does it look like. However, we can do that somehow when we are in a current location, like, for example, if I would fire HoloLens right now here, we can connect to HoloLens and fire up device portal, which is a small server that is running on HoloLens. And on a special tab called 3D view, we can actually see the nice green shaded visualization of our current location. But this is current location only. And that view actually gives us a little bit of idea of how the scan data looks like. It's not for regular users. It's mainly for developers to get a grasp of what is going on, or for debugging. We have this nice white ball and the frustum rendered so that it shows where HoloLens is in this location and which direction is it looking at. And the cool thing here is that we can export that model, because that's basically, we can export it as like a regular Unity object, and we can import it in the into Unity editor, so it allows us to develop without HoloLens device at all. Basically, we can emulate this location inside our Unity editor, which is very cool and helpful. Actually, when I discovered that, I stopped using HoloLens when developing applications. I mainly use it when I really need to test something out in the reality. So, so how exactly can we use the data? Because I'm telling that there's a lot of data being gathered. So how to gain access to this data? How actually use those data in our application? So there, we have to do some coding to make that happen. And Unity API, scripting API, delivers the several objects, the classes that can help us out. One of it, and the most important one, is Surface Observer. That's the thing we create, at least one, for our application if we want to use spatial mapping capability. And this is the thing that, well, we need to configure on how to react on all those spatial data that is being gathered. So the first thing we define is something which is called spatial volume. And spatial volume is basically like an area in the 3D space, like invisible area, that we tell the Surface Observer to get us updates only from this area, and anything else doesn't matter for us. So we can define some kind of a focus area for all the updates that we are interested in, so that we are not wasting computational power for anything which is outside that volume. And those volumes can be different shapes. They can be box, sphere, or frustum, and they can be word locked, attached to one particular point in our game world, or body locked, so we can follow the user. So we can imagine here, for example, one scenario where the gameplay or the application wouldn't require a lot of movement of the user. So we could create like a word locked, box shaped spatial volume that would be like an invisible box, like for example 5 meters by 5 meters or 10 meters by 10 meters, where all the updates will be coming from, and we would simply ignore all the other ones. And for example, in the other scenario, which would involve more users' movement and head movement of the user, then we would like to have those updates that from areas where the user is actually looking at, and the user is walking a lot and looking a lot, so that box-shaped spatial volume wouldn't work out pretty well here. So in this case, for example, we could create, for example, the frustum-shaped body-locked volume, so that it would be frustum-shaped, which means it would kind of mimic the user field of view, and it would follow the user, so that we are getting updates only from the area of interest for the user. It really depends on the scenario. There are a lot of different approaches here. So basically, when we have our spatial volume defined, we can register for surface changes. That's basically, that's separate of what I told before. I mean, the thing that is happening on the operational system level, it's still happening under the hood. Right now, we are setting up the object that would poll or query that operational system data. So we are registering for updates, and then we are getting some events, or we are polling for the changes, and we are getting events like surface added, surface deleted, or updated. And it's up to us to react to those events. And I mean, it's up to us to define what we're going to do with those. So, for example, if the surface is deleted, then we simply have to delete it or cache it or hide it, whatever. But when it's added or updated, we can request, or we should request, something which is called mesh. We already seen the mesh at the morning session. So basically, we are requesting the mesh to be created for us, and we can define the mesh resolution. So, for example, how many triangles has to be involved in that mesh creation. And that's also, I mean, usually we're using 500, but it really depends on the scenario, 500 per square meter. And also we can define if we would like to have colliders baked into that mesh. Colliders, I mean the regular Unity colliders, which are used for physics or detecting when we are entering some area. And after that, when we get that mesh, we can simply render it. So it looks like this, and we already seen that on the morning session. So basically, that's the mesh that mimics the location that has been scanned, right? And we don't use it in real application because that could be tiring or just simply not useful. But that shows us, I mean, the actual data that has been gathered and processed by our surface observer. But the interesting thing here is that, I mean, that's the white wireframe is just a material that is applied to this mesh. We can simply remove that material and we won't see it anymore. But the important thing is that along with this mesh, we have colliders baked. I mean, if we request that we want colliders. So the whole visualization of user's surroundings will be covered by invisible to the user colliders. So that can give you an idea what is it for. I mean, all the physics interactions, all the placing of holograms, or whatever we can imagine that we would like to interact with real surfaces, that's possible because of those colliders. So whenever there is a floor, there is a collider on the floor. So whenever there is a virtual ball that we have here and we'll drop it, it will hit the collider. And there we will get that effect that the floor is actually interacting with the virtual ball. Of course, I mean, mesh colliders aren't like the most performant ones in Unity. Actually, they are the worst ones, but there is no way of mimicking these complicated surfaces with those simple shaped colliders like spheres or capsules or boxes. So we have to deal with that, but this is not a big deal. And we can live with that. So that's the kind of magic behind of creating the spatial mesh. And it's not all sunshine and rainbow, I would say, because the scanning process isn't perfect. The sensors aren't ideal. They have their shortcomings. It's easy to introduce some errors into our spatial data that we gathered. So there are some most common affecting factors that affects our scanning process and resulting mesh. So for example, user motions. Whenever, as a user of the application, we walk a lot and we turn our head a lot, it's obvious that the surface observer wouldn't keep up with all the, I mean, not surface observer, but the HoloLens. It wouldn't keep up with scanning everything so fast. Surface materials, whenever we have like a solid color walls, for example, without any features, it will take more time for HoloLens to detect that surface because it doesn't have like special features on this wall to detect where that wall is and what angle is it from the user. So that to detect that solid color wall, for example, we would have to look at it from different angles, for example. So surface materials matter. Scene motion. We can have moving objects inside our scene. We can have like people walking around or pets running around, and all of them will be scanned at some point to some extent, and this can introduce some extra mesh that is not actually there and shouldn't be there. Also, lighting interference. So whenever it's too bright or too dark, there are also errors involved because when it's too dark, basically we can't scan. So the most common scenario, as I've experienced, is usually the corners of the room, because we usually do not walk pretty close to them, and they're usually darker than the rest of the room, and that's where the holes in the spatial maps usually appear. So those affecting factors, and many other, I guess, but those are two most common. They can introduce some errors in our spatial data. Namely, first are holes. Holes are basically not completed mesh. So we can have like for example, if we wouldn't scan the floor, the full floor in details, we could have some holes there. And if we wouldn't deal with those holes, we could have, for example, a hologram jumping into that hole, and it would disappear from our world because it would just fall into the void. And hallucinations. Hallucinations is the spatial mesh that does not have the corresponding object in the real life. So we've seen that on the morning session where I think Piotr was standing in front of HoloLenses and it was scanned. We have seen the mesh of his person, and then he walked away, and that mesh was there for several seconds still. So that was the hallucination, because there was no corresponding object for that spatial mesh. And also biases. This is where we have mesh which is not well aligned with with the physical surface. So we can, depending on the scenario, of course, we can deal with all those problems, or at least with most of them. And that's where usually applications which require a good spatial data without many errors, they introduce something which is called room scanning experience. So whenever you fire up the application, you have a moment, and usually the application asks the user to walk around the room and look at the walls, floors, and corners. And there is usually this nice visualization of the mesh floating around the walls to let users see which part of the room is being scanned. And that's the part of the application where we are making sure that the user actually walks around the room and gather some more data for our application. That's actually one of the best practice. It's not like we should that or something like that. I mean, all good applications that use spatial data to full extent, they usually have this element of a startup. So when we have the spatial data gathered at some point, we might want to just leave it as this because, for example, we might not care about those errors. For example, we don't care about like small holes or whatever, but we might want to do something more with spatial data. For example, we might want to detect where is floor. We might want to smooth the floor. We might want to detect walls or smooth walls or etc. Or find some shapes in our on our spatial surfaces. So that's where spatial understanding, which was mentioned in the first session, comes into play. So basically, developers from Asobo Studios, which is the partnering company with Microsoft, when they created this Young Conquer game and Fragments, they recognized several patterns when they were creating those experiences, so that the patterns with spatial mapping data. And they noticed that they're repeating some scenarios pretty often. So what they did, they packed it up and they released this, those functionalities as a open source project, which is part of the Holo Toolkit, which was mentioned as well by the guys in the morning. With this spatial understanding module, we can do a little bit more advanced processing of our spatial data gathered. So for example, we can have this room scanning experience where we basically can see how the scanned area of the room is being covered by the mesh, the spatial understanding mesh, and you can't probably see it here, but we can get more statistics out of the scanning process. Basically, the module can tell us how much floor we scanned or how much walls we scanned. So we are actually also getting some more information about those surfaces because it can detect that this is probably the floor or the wall, etc. So this is really helpful in some scenarios. With those information, we can, for example, cast an array somewhere into our spatial mesh, and we can get an answer which will tell us this is the wall, and we don't have to do it ourselves. I mean, this module has it already implemented. Also, we can do, based on that, we can do some topology queries. That's basically, we can ask the module, give me the biggest wall in the room. Because, for example, in our application, we would like to put some holographic windows there. So we would like to have like a biggest wall in the room for some reason. And the other ones are shape queries. That's something where even more sophisticated, because we can ask the module for seatable areas, and it will give us all the places that the module thinks are seatable. I mean, chairs, sofas, or beds. And that's something you can really see in the Fragments game, because there is one person there that walks into the room, and it actually can sit on your sofa or on your bed while you're playing that. So this is really, really awesome and gives you that immersion effect. Pretty cool, pretty good. And also we can detect sofas in, for example, the query for the sofa is like, give me the platform which is I mean that high from the floor, and the other one which is like the upper part of the sofa somewhere here, and it thinks it's a sofa, and it will look for those kind of platforms in our spatial data. And the most advanced part is placement solver. That's basically mainly used when we would like to have some procedural place space generation. So, for example, we can request something like this: give me 4 box-shaped areas, each box 1 by 1 by 1 in meters, that would be near me, and every box should be 2 meters away from each other. And that solver will try to find those areas, and we have them nicely visualized here, but we can obviously just render some objects there. So for example, we might want to write a game where we would like to have some city, for example, generated on our floor, and we can use this module, for example, to find those places, perfect places for our buildings. So all of that, all the technology involved and all the software that has been created, it allows us to create really cool effects in our applications. regarding spatial mapping. So let's just overview. Whoops. Let's overview some of them. So it can give us, it can help us create navigation for our agents, for example. So whenever we have an agent in our game, for example, that should run on the floor or on the table, it can actually behave as the real human being by avoiding all the real obstacles, or jumping over some holes, or jumping over the table, for example, because the application knows that the table is actually there, knows that the table ends at some point, and if the agent would move there, it will fall down. So it would add up to the whole experience. The next thing, I mean, that's my favorite one, is occlusion. So the virtual content can occlude real-world content and vice versa. The real-world content can occlude holograms, and that means we can see here that this first case, that the virtual content actually occludes the sofa, but it can work the other way around. So, for example, we can have a virtual object that we put in this room, and if we would go to another room, that object would disappear from our side because, for example, it's now hidden behind the wall, obviously, right? So we can feel that this object is actually there, and it's also occluded by real object. It also allows us to apply some cool effects to it, because sometimes we would like to hide objects from the user, for example, behind the wall, but we would like to still let the user know that this object is actually there, because sometimes when you have lots of holograms and you hide them, there's no way for the user to find them, right? So, for example, we can apply different materials or shaders to those objects that are occluded, so that, for example, they appear to be, I don't know, blurred, or they just render in different color, or just render the wireframe or whatever. So this is very cool. The other thing is physics. That's the thing I already mentioned. So we have those colliders baked in our mesh, spatial mesh, so that every object that we have in our application can physically interact with those colliders, and we can have the balls bouncing on the floor, we can have our agents hitting the sofa or wall, and that also gives this immersion effect that this is really happening in our location. And the other thing is placement, which means because of all those colliders and mesh that we have, we can actually place all the holograms wherever we want, and we will be tricked into thinking that those holograms are actually sitting in those positions. And also we can cast shadows to even adapt to this effect, or put some glows like we can see here, so that we really think that those holograms are there. And that's all because spatial mapping functionalities and how they are delivered with HoloLens. And that will be it, 45 minutes. So I think that we have 15 minutes for questions. Thank you.
Questions, please raise your hand so I can give you the microphone.
I would like to ask, what's the resolution of this tracking of the placement of the holograms in the real world?
Resolution of placement?
Yes, because earlier we could see that when there was this I don't know what it was. It was some animal hologram placed on the floor. When user was walking around it, it jittered a little.
Well, it depends. I mean, it's. If
just
it's
ballpark, is it 3 centimeters or 5 or?
I have no idea, to be honest. I mean, to avoid jittering, the developers had to use something which is called word anchoring, and if you word anchor the hologram, then it should stay at this point. If you would anchor the hologram here, it should sit here. And if we would not anchor the hologram, if we would not use the word anchor, the more we move and the more the application learn about surroundings, then we can introduce some jittering, because that point would be floating, because the HoloLens might learn a little bit more about what's happening on the surface between me and the hologram, and that's where the jittering is usually introduced. So thanks. I don't know.
And I've got another question. What is the frame rate of this spatial mapping?
Frame rate of how quickly it gathers information?
What's the frequency of?
I don't know. I don't know. To be honest.
Okay.
I would have to check it.
Thanks.
Thanks.
Hello, I have this question. 6 months ago, I was able to test HoloLens, and I noticed that, at least in my device, the generated image was laterally translucent. I mean that it wasn't so deep and vivid like in the images which was proposed on the slideshow.
Well, yeah, I mean, I've noticed that as well. I mean, when we use HoloLens, usually the transparency is a little I would say it's the objects are more transparent comparing to what we can see on pictures and videos. I don't know what's the reason. I mean, we can control it somehow, but there will always be somehow transparent-ish.
I may extend a little bit this question, because how do you think, when will be this technology so advanced that we will have this resolution of images, this intensity of this image comparable to, for example, sci-fi movies? Okay. I understand that.
Yeah, I know what you mean. Well, with HoloLens, the problem is that, in my opinion, we still have to think about this device as some kind of a prototype, because, I mean, it looks nice, it's released, you can buy it and stuff, but it's still like the first version, and there's no competition on the market. So I think they don't put like everything they could into that device. So I think like way more is possible, but we still have to wait some time, because I mean, it's still like there's no competition. So what's the point in pushing it forward, right? I mean, that's how it works, right? So I think it's possible, but we have to wait. And I mean, they also had to do some trade-offs, in my opinion, because I mean the device is expensive, and they had to think about stuff like, what kind of resolution should we put? What kind of lenses should we put? That's why we have the narrow field of view, for example. What kind of batteries should we put? And all of that, I think all of that caused that we have this and not other kind of device. And I think, given the circumstances, it's good enough for the time being. I mean, we still have to wait, I guess. I hope that answers the question.
Okay, there.
Having read the topic of this presentation, I was expecting to hear something about the mapping process itself. So how the mesh is constructed using having the data from all of the sensors. Could you maybe explain briefly how the...
Well, that's a black box for me, I would say. I mean, that's what happens inside Unity. So I have no idea, to be honest.
The code is not like open, or
well,
the algorithm is closed.
It's Unity, so it's not open sourced, right? I guess. Okay. I mean, all you do is you use Surface Observer and you asynchronously request a mesh. I don't know what happens under the hood, to be honest. And I mean, that's from Unity API. So whatever Unity provided there, it's there.
And are there any publications? What do they use to
maybe
the mesh?
I don't know. I wasn't drilling into that into those details, to be honest.
Okay, thank you.
Thank you.
On that demo that you showed, the floor and the couch, they clearly had different physical properties. So I wanted to know if this is based just on a guess, based on what the shape looks like, or is there some other way
demo?
of detecting
Oh.
what the material is?
Wait a second. Which picture was that?
The last demo, there were balls. One ball was on
This
the
one?
couch, and it was moving differently than the balls on the floor. So is it just based on this, that the floor is a big flat surface, and you're assuming that the surface is hard, and yeah.
Okay, I don't know what is happening, but I think I know what you're
Yeah,
what you're trying to say. So, well, it depends on how how developers process that mesh. So they might, for example, replace the mesh that is on the floor with like completely flat plane, and that would be completely flat, and the surface on the couch, for example, could be like a bumpy mesh, and that's why whatever will hit that bumpy mesh would act as it's not on the flat surface, right?
Yeah, I get that, but if there was a chair, for example, in a shape that would be similar to a couch, would that result in that ball behaving on it, bumping in bouncing in the same way as on the couch, or is there some more?
It depends on the what you will do with that. To be honest, I mean, it depends on what kind of. I mean, you can process the surface a little bit more and make it smoother or flatter. So it really depends.
Yeah, but I just mean how you distinguish between the surfaces, because yes, it's your choice. The way the objects are acting on those surfaces, and then you pick the surface that you are going to use for this.
So how you distinguish between sofas or?
Yeah, if it's just based on the shape and.
Yeah, I mean that's how it's implemented in spatial understanding modules. So if you want to use that, you're you're counting on how they implemented that. So. So you can always implement it by yourself. You can define surfaces that you're looking for and just process the mesh by yourself, right? It's not like the part of like Unity API. It's a spatial understanding module, which is something else. So it really depends on how much work you would put into it. And with spatial understanding, you're dealing with something which is done by some people, and they define suitable areas in that way so that they're being detected in that way and not another. I would say.
Okay, thank you.
I have a question, because at the beginning of on a few first slides we can show some polygons, very unregular. What was the result of the spatial mapping? Yeah, this shows some room with some unregular. Oh, for example, that one which you are.
Wait a second.
This one, yeah. As we can see, this is really unregular. Yeah, we have a lot of different polygons, and on a few next slides, we have really regular mesh.
Wait a second. You mean this one?
This one.
Okay.
This is also from.
This is spatial understanding, and that the first one was spatial mapping. So this is something built on top of spatial mapping. This is from that other module, which is called spatial understanding. So this is like processing of that mesh.
And this is also delivered with this library?
Yeah,
okay, that's great.
Because what happened here actually, this is visualized pretty nicely, but here what we can't see, the module is actually built in like the 3D invisible objects, which are called voxels, I think, in that case. And they every square, it's like 8 centimeters by 8 centimeters box, and it lives at every cell here, and it contains even a little bit more information. So, for example, when we have this box here, or the square here, and there is this invisible voxel as well here, it contains already some information about what kind of surface the module thinks it is, for example. So this mesh is different than the other one. It's the processed one already.
Any more questions?
Well, I've got another question about this resolution and stuff. does the change of you said earlier that you use about 500 polygons per square meter, right?
Yes.
And does changing of this resolution and spatial volume affect the frequency of the mapping? My question is, can you walk faster if you lower your resolution?
No, we can't control how the HoloLens is gathering data.
Okay.
We can only control how we are using those
so
data.
it's not affecting those algorithms.
No, I mean, Surface Observer works on top of the data that HoloLens gathers on the operational system level.
All right.
Below that, we're not able to do anything.
I thought that this spatial volume was changing some things in those chips or something.
No.
Which do this ability. Thanks.
Okay.
Questions? I don't see any hands.
I think that's it. Thank you very much then.